My name is Vikram Saraph, and I'll be talking about an empirical study of speculative concurrency in Ethereum smart contracts. This is joint work with Maurice Herlihy at Brown University. So I'll start with an overview of this talk. I'll go over just some motivation and, of course, the basics of smart contracts, and then some previous work on adding concurrency to smart contracts. And then I'll talk about applying a speculative technique to historical transaction data on the Ethereum blockchain. And then I will talk about the methodology that we do in order to do this. And then I'll talk about baseline experiments that are used in order to evaluate this technique, and then some alternatives. So to begin with, I'm sure most of you know, Ethereum, like Bitcoin, consists of a blockchain with blocks that contain a bunch of transactions, and miners attempt to add new blocks of transactions to the blockchain, and validators attempt to verify the authenticity of each block. So unlike Bitcoin, Ethereum transactions may be more complex than just value transfers. Ethereum comes with these objects called smart contracts, which are long-lived objects with attributes and methods. And these smart contracts can have functions that may change the data of these smart contracts over time. These smart contracts live on the blockchain, and they are implemented in some sort of assembly-like language, which is just referred to as EVM bytecode. So it's natural to ask then, since we're basically, smart contracts are basically just executing code, whether we can take advantage of the multiple cores that modern day architecture possesses. The problem with this is that you can't immediately apply concurrency because the Ethereum virtual machine is designed as this sort of single-threaded virtual machine which executes transactions sequentially. So, for example, it's not generally possible to just execute transactions blindly in parallel by assigning each transaction to a thread or a process, because there could be race conditions between these transactions. There could be dependencies. So we have to think about this. So, for example, some transactions have to be serialized due to data dependencies among certain transactions. We can't run them in parallel because we could possibly get non-deterministic results when the validators come along and try and re-execute the same thing that the miners did. So there was previous work by Maurice and another of his students that was presented at PodC in 2017, which was about adding concurrency to smart contracts. Basically, the idea here is that they applied techniques from software transactional memory, and since executing smart contracts is basically just executing code, so they applied this notion of software transactional memory to execute smart contracts in parallel, and this accounts for the sort of data dependencies that I had talked about. Just at a high level, their technique that used software transactional memory, it takes a block of transactions and executes them via software transactional memory, and then it produces this directed acyclic graph with all these dependencies among the transactions within the block. And then this is made available for the validators, because the validators need to re-execute the blocks in the same kind of order. So in the original work on this adding concurrency to smart contracts, the work was tested on a synthetic workload of 3 unique contracts. And since there isn't software transactional memory available for running Ethereum bytecode, what they did in this paper was instead they took some Solidity contracts and basically translated them into Java, and then applied Scala STM in this case, and then looked at the results that were obtained in this way. And what they got was, with 3 threads, they saw a speed up of 1.69x. But the one big issue here is that they worked with synthetic workloads, and such a workload could be more uniform than what we see in practice, like on the historical Ethereum blockchain. So it's a natural question to ask, well, what would you get if you applied similar techniques on the historical data? So that's what this work aims to do. So I'll briefly talk about I'll describe the historical Ethereum transaction data that we worked with, and then I'll continue to the methodology that we use to use this data to simulate our speculative techniques. So, as I said before, the main question is, what if we applied this concurrent speculative execution technique to historical Ethereum blockchain transaction data? So the idea here, what we want to do is we want to take transactions that were part of the Ethereum blockchain and look at them and try and re-execute them in some way in a speculative manner. The problem here is that, the immediate problems are that, like I said before, we don't have software transactional memory available to us. So we have to go with something more simple because we don't want to implement a complicated system here. We want to go with whatever is available to us. And then, of course, we don't have a concurrent EVM either. So we have to work with that limitation. So the idea is that we take this historical transaction data and we simulate what would have happened if we instead re-execute those transactions in parallel using some kind of speculative technique, which I will describe in the next few slides. At a high level, the way we do this is by looking at the transaction traces of the original transactions on the blockchain when they were sequentially executed. And then we basically play them back in parallel. So the way we obtained the transaction data was using this Go Ethereum client, which was mentioned in one of the previous talks, to basically synchronize and download the blockchain. And we obtained data up to December of 2017, which is close to when there was peak activity on the Ethereum blockchain and with cryptocurrencies in general. But we were limited in the data we could get because it takes a very long time to run this client and synchronize it. We required what's called an archival copy of the blockchain because this is required in order to calculate traces using the Go Ethereum client. And synchronizing it in this way is actually slower than just the growth rate at which the Ethereum blockchain is growing, just to give you an idea of how slow it really is. So there are too many transactions to analyze all of them, so we focus on certain subsets of the data that we have. Specifically, we look at 7 historical periods between the time range of July 2016 to December 2017. And basically, these are 1-week periods where the periods are separated by 11 weeks each. We chose the number 11 so that we can see all parts of a month, early in the month, middle of the month, later in the month. So as you can see, the number of blocks in these periods basically ranges from 3,000 to 4,000. There's a clear increase, though, in the number of transactions over time, especially in period 7, which will be an important distinction later. As I said before, there's a lot of data to work with, so we went with 1 in 10 sampling of blocks. We just looked at 1 out of every 10, but just as a sanity check for one of the historical periods, we compared 1 in 10 sampling to full sampling, and the results were quite similar. So we're confident that that's good enough. So the So basically here we have a plot of the transaction activity of Ethereum over time, and the red intervals are the intervals that we looked at. The transaction activity is measured in the number of transactions per day. So as you can see, it kind of peaked between 2017 and 2018, sort of around the new year. And this graph only goes up till August of 2018, but it's pretty much been around that level since then until now. So I'll now talk a little bit more about the smart contract language and what we have exactly to work with, the data that we have to work with. So I'm sure as many of you know, Solidity is a popular language for implementing smart contracts. It's a high-level language, and it's more friendly than working with the bytecode directly. However, it's the EVM bytecode that's officially part of Ethereum and part of its spec. So this is what's stored on the blockchain. We don't have access to Solidity sources. So we have to work, since we're working with historical data here, we have to work with the bytecode that's on there, and we can't really work with any sort of higher level language as was done in the previous PodC paper. So basically, as I suggested before, the idea is to get these traces using this Go Ethereum client, which provides a native tracer. Get these traces, and then we want to simulate the execution by running these, stepping through these traces in parallel. So I'll go into more detail about how exactly you do that, although it's a pretty straightforward technique. So before I get into that, we need to I need to talk more about what exactly we mean by data conflicts here. I kind of just vaguely mentioned it before, but I'll define it more concretely. So in general, two transactions commute if any interleaving of them results in the same global state. If that's not the case, then they conflict because it's possible to get two different states. And then at a more granular level, we say that two bytecode instructions commute if they can be executed in either order and you get the same result. So what exactly do we mean by global state of the Ethereum blockchain? Well, if you go and look at the yellow paper, basically all this means is the state of each contract. And the state of each contract consists of the balance, the bytecode associated with it, which is unchanging, and the what's called the persistent storage, which is basically a key value storage that is that each smart contract possesses. All other state mentioned in the yellow paper is transient. It only exists, it's private and only exists during the execution of the transactions. So this is basically what we focus on. So given that this is what the global state is, we now look at what are possible conflicts that we can determine by just looking at the bytecode. So the most obvious one are the sload and store instructions, which are basically reads and writes to the key value storage that the smart contract possesses. So if you're loading and storing from the same address, then of course that's a conflict, and they don't commute. Other possible ones are contract creation and calling the contract that was just created. Of course, if you try and call the contract before it's created, say within the same block, then there are going to be issues. And then a third possibility is with balance reads and value transfers. So, for example, if you try and send some ether and then read the balance, then there are possible issues there with commutativity. So the idea, given these transaction traces, since we don't have software transactional memory, again for EVM bytecode, we just use this simple strategy of simply greedily executing all transactions within a given block in parallel. and look for conflicts along the way. And if any transaction raises a conflict during its execution, then you just abort that transaction and defer that transaction into a subsequent sequential phase. So for example, transactions 3 and 5 say they have conflicts and they abort to the sequential phase. So given a set of transactions within a block and the sequence of bytecode instructions, the traces that we get from the tracer, we basically just randomly step through each sequence of bytecode instructions associated with each transaction. And as we do that, we keep track of load and store operations. So I should have mentioned this before, but the load and store conflicts are actually the ones, the kind of conflict that are by far the most common. The other ones are basically hypothetical scenarios, but they, in practice, happen very infrequently, so we just focus on the load and store operations. So given these traces, we step through and track the load and store operations. And at each load or store, we basically try and acquire a read-write lock associated with the location that it's trying to access. And if it was successful in acquiring that lock, then there was no conflict and can continue its execution. Otherwise, if it failed to acquire the lock, that means that there was a conflict with some previous access by some other transaction, and the transaction then has to, you stop that transaction and it has to be aborted to, it has to be deferred to the sequential phase. And of course, as in similar to like a two-phase commit protocol, during the parallel phase of execution, you cannot release any locks until the parallel phase is over, because, again, there are issues with validators possibly obtaining different results if you release the locks too early. So one thing that, so our principal measure of evaluating this technique is speed up, but in order to do that, since we're looking at traces, we don't really have a concrete measure of time to work with. So if we want to measure speed up, then we need some kind of measure of time. So basically the heuristic that we use for measuring time in this case is to just look at the cost of the amount of gas that each transaction uses over the course of its execution, whether it aborted or succeeded. One alternative, which I bring up later, is just to count the number of instructions that are executed by a transaction. But since we don't have a concurrent EVM, the whole point of this study is to do all of this analysis without a concurrent EVM. There's that inherent limitation. Now, given the technique and the data, I will now talk about the results of applying the technique to the historical data. I'll start with the baseline experiments. So we have two figures here. One is the average speedup over these historical periods 1 through 7. And we run the experiments for 16, 32, and 64 simulated cores. And on the right-hand side, we have the same numbers for the conflict rate, average conflict rate over these periods. So as you can see, the speedup starts out high in in intervals 1 and 2, starts at 8x at 64 cores, but it goes all the way down to 2x for 64 cores. And likewise, the conflict rate goes up over time. So looking at the very high conflict rate in period 7 kind of suggests that that's probably one of the reasons why there is such limited speed up in period 7. Then we further analyze the speedups by looking at the distributions, the speedup distributions for the blocks. So here we have periods 5, 6, and 7. I only look at 5 and 6 because previous periods have similar distributions. But it's pretty clear that 5 and 6 have heavier tails here, so there are more blocks with higher speed up. But period 7, it fails to, well, it's more concentrated between the interval in 1 and 2 because, again, not as much speed up is realized. Then we look at hotspots. So informally, a hotspot is an address in persistent storage with many conflicts, but how many conflicts is a parameter they can choose. So instead, we look at these sort of distributions of hotspots. Basically, the way to read these graphs is that there are Y unique addresses with exactly X conflicts. So for example, in period 5, there are 2,500 addresses with exactly 2 conflicts. And the thing to notice here is that 5 and 6, again, they have similar distributions here, but period 7 has a much heavier tail. That suggests that there are a lot more points of contention within period 7. So the possible reasons that you could get that there is low speed up in period 7 is that there are many calls to high conflict contracts that are just inherent to the contracts. For example, there are a lot of tokens that came out around this time, and it's reasonable to believe that tokens are going to be highly conflicting because they're probably going to have a lot of shared variables that are updated with each call to the various functions. Another possible reason for low speedup is that in practice you have non-uniform workloads as opposed to the synthetic workloads that were used before to evaluate this. So, for example, if you have one long transaction and a few short transactions, and you're not going to be able to achieve a lot of speedup. And of course, another reason is you simply have too few transactions in your block. If you take a look at any blockchain like Ethereum Explorer, then you'll see that there are still a lot of blocks that have like maybe 2 or 3 transactions in the block, so you're not going to be able to achieve much speed up if that's all you have to work with. So now I'll talk about some of the alternative experiments that we looked at for this technique. So one idea that we had was to look at, instead of just doing one parallel bin and then a sequential bin, we thought we might try out multiple concurrent bins before deferring just to sequential execution. So while in theory this could work out for certain workloads, in practice, given the historical data, we can see that this generally results in a minor decline in speedup if you increase the number of parallel bins. So it's probably not worthwhile to, you're not going to get any more parallelism by introducing more parallel bins because what you're left with is probably highly conflicting anyways. Another thing that we looked at in our alternative experiments is looking at exclusive versus read-write locking for the load and store instructions. So this actually has quite an impact on, if we replace the read-write locking that I described before with exclusive locking, then you see a significant reduction in slowdown. So this suggests that if you're going to be implementing something like this, then you should definitely be using read-write locks. And then we looked at the two different, a comparison of the 2 different heuristics for time that I mentioned before, which is gas cost versus instruction count. So there are some minor differences here, but the general trend remains the same, which is promising since it suggests that this is at least a good way of, this is probably a good way of evaluating how long each transaction takes to execute. again, this is what we have to work with since there's no real way of measuring time without a concurrent virtual machine. And then another alternative experiment we looked at was, well, what if we assume that we can just look at the transactions in a block and just statically determine whether a transaction will abort if you can just look at the transaction and determine whether it aborts. If you can do that, then there's no point in running the transactions that you know are going to abort. And so if you assume that you have this ability to statically predict, you get some minor improvements in speed up, especially towards the end of the historical periods, like period 7. But in general, this kind of suggests that maybe it's not worthwhile to just look at static conflict prediction for this sort of technique. And one more experiment we looked at, one more alternative experiment was just simply removing the calls to CryptoKitties in the time interval 7. I noticed that when I was looking through one of the Ethereum explorers that there were a lot of calls to CryptoKitties around that time. Like sometimes blocks had like 50% calls to CryptoKitties. So I just thought I would just drop them. And I did that, and I looked at what was the result of this hotspot distribution that I showed you before. And as you can see, just removing this one contract makes the hotspot distribution resemble that from periods 5 and 6. So this suggests that it could be worthwhile to focus on a small number of contracts, in particular something like CryptoKitties. And the last experiment that we looked at was to just ignore, based on what we saw from CryptoKitties, just ignore highly conflicting contracts. In particular, for each time period, we just dropped the top 5 most conflicting contracts and ignored them and reran the experiments. And you can see that there is quite a noticeable increase in the speed up that's achieved. So this suggests that maybe it's worthwhile focusing on just specific contracts and seeing whether you can improve them or make them more friendly for concurrency. So to conclude, this kind of technique works, the simple speculative execution technique works well under low contention, as we saw in the earlier historical periods, although it gets worse in later periods, so that suggests maybe it's worthwhile to analyze the highest conflicting contracts and focus on those specifically, and maybe draw inspiration from those to maybe like add new bytecode instructions to your to the EVM bytecode language. For example, maybe you could add like a test and set operation, because it's probably common for these token contracts to either increment or decrement a lot of shared variables. So if you introduce some kind of atomic test and set operation, then it would remove a lot of conflicts that would otherwise be inherent to some of these contracts. Thanks.
Questions? There's one over there. Go. Just a question in the meanwhile. So what is the difference basically from gas consumption and the count on instructions? Because this is the EVM, right, that actually counts the gas consumption.
Right. So if you just look at instruction count, then of course all instructions are equal cost. But if you look at gas costs, then there's actually some significant variation between, say, like a store operation, which costs like on the order of a few thousand, to the arithmetic operations, which are like 2 or 3 gas. So in that sense, there's a difference.
Thank you.
Hi, thank you. I was wondering if you had more of a general opinion on how ETH and public blockchain can scale, because it seems that maybe because of their nature, public blockchains have a lot of trouble scaling, sharing everything with everyone. And so maybe we have some great dApps that are going to come up, but maybe the ETH network won't be able to handle the load.
Your question is about
Just general scalability of public blockchains, and like what do you think could be done?
Well, I guess from the perspective of smart contracts, the smart contract side, focusing on that, I think, again, these concurrency techniques would be helpful in reducing the time it takes to run these smart contracts. And so I think it'd be worthwhile to focus attention on that through studies like this. But I think the other side of it is, of course, the cryptographic puzzle issue or the proof of work, which is basically an independent from this kind of work.
So maybe we can ask a question to the speaker during the break. Sure. Okay. Thank you very much. So.